So hello everyone. Today I am going to tell more exciting things in the world of AI and blockchain. Okay, how do we trust AI models which are running on our computers that we don't control, right? So imagine like I want to use a powerful AI model, like you want to use a powerful AI model, and you are worried someone might steal your data or tamper your data. Like that's what I am going to explain today. Okay, so I am going to walk through my report paper on trusted execution environments for decentralized AI. So this only focuses on Sentient Enclaves framework. So before I jump in, I'll give a quick disclaimer about this video as well. This is an independent research and for educational purposes. So I have no relationship with anyone which have been mentioned here. Okay. So the technical details come from publicly available sources and from the academic research. So let me give you the context. So this paper analyzes how we can run AI models securely in decentralized networks. That means where we can't trust the infrastructure operators, right? So think of it putting your AI in a bulletproof vault or bulletproof thing that even data center owner can't peek into like that. So right now, if you train an expensive AI model, suppose maybe you spend some millions of dollars on it, and you won't let others use it in a decentralized network, then you will be having a big problem. What is the problem? Like how you prevent someone from stealing your model weights, right? So how do you users know their sensitive data which isn't being logged? So how do you prove that the AI is running the correct code and not someone modified versions, right? So this will be the one of the bigger questions. So traditional solutions rely on trust, like you trust the cloud provider or you trust the node operators. But when it comes to decentralized systems, we can't make those assumptions. Okay, so we need something stronger. We need something more impactful, right? So that's where TEE comes. TEE means trusted execution environments, full form. So these are some special hardware-based security zones. Like they create some isolated environments where even the operating systems or even cloud providers can't see like what's happening inside. If we, it's like having some secure vault which is built directly into the processor chip itself. So now let's look at the different TE technologies that are available today right now. So I put some gather. I have taken some multiple data resources to show you exactly what each platform can do. So when you look at this table, we are comparing Intel SGX, we are AMD, even Intel TDX, AWS Nitro Enclaves, and even ARM Trust Zone, which are some multiple dimensions. Okay. So first, the when it comes to architecture type, Intel SGX is process based. Okay, like it creates small isolated enclaves within applications. But the main thing is it has only 128 to 256 megabytes of encrypted memory. That means there's like some limitation when it comes to enclave page cache. So for modern AI models which have billions of parameters of model, this is too small. It doesn't fit. So when you look at the VM based approaches, that means virtual machine based approaches, AMD SEV-SNP, which is another one, and Intel TDX and AWS Nitro, they can handle up to 512 gigabytes GB. That means gigabytes, 512 GB. So that's why they are marked as supporting, like they can support 7 billion parameter model or 13 billion parameter model, or even they can support 70 billion parameter models as well. So when you use this INT8 quantization, okay, so the performance overhead is really interesting too. That means VM based TE shows 10 to 25% overhead of AI interface. That means if your if your model normally takes 100 milliseconds to run, it may take 110 to 125 milliseconds in TEE. So that's actually pretty reasonable for the security that you are getting. But here's where it get tricky is that Intel SGX it shows about like 74% performance losses for memory. Okay, so you may ask why? Because when you exceed that tiny page cache, so the system had to swap data in and out. This will kill the like the performance. Okay, it will suck. So the key takeaway from this table was even to deploy like LLMs, that means large language models in a decentralized networks, virtual machine based TE is like AWS Nitro, which is a good choice. So they have some capacity, like memory capacity. They even run some real world AI models as well. So when you look at, let me show you something like another important table or a figure for memory requirements for AI models. Okay, so this graph shows memory requirements across different model sizes with some formats. So here the x-axis shows the model size like 7 billion parameters to up to 175 billion parameters like that, and the y-axis shows how many memory we need in gigabytes, that means GB. So when you see these three lines, the top one which is FP32, which is in 32-bit floating point precisions, that means like a 7 billion parameter needs some 28 GB just for weights. Okay, so the middle line is FE16 which have some 14 GB, and with the bottom INT8 quantization gets down to like 7 GB. So when we look at these horizontal bars, so the red line at the very bottom, which is an SGX 256 megabyte limit, like it doesn't even show properly on the scale because it's too small. So the green line shows what's practical with the AWS Nitro on the standard instance, so around some 100 GB. So even the blue line at the top shows some maximum with large memory with some instances also. But what I discovered here was like you need to multiply the model weight size by 4 to account for activities like during inference. So the 7 billion parameter model, that means the INT8, it needs some 7 GB for weights. That means you actually need around 28 GB memory to run it safely. To run safely you need 28 GB. So like this is why everyone say that 7 to 13 billion parameters are some good region for TEs, and 70 billions are like it isn't challenging part, and beyond impractical also like it may go. So when we look at the real world performance, because numbers on paper are one thing, but when we measured over it is what matters, right? So this bar chart relatively performs across different workload types. So in the execution part, which is our 100% baseline, so for CPUs intensive workloads, Intel TDX is good, perfect, not perfect, good, better, which is as like 92% thing. When it comes to AMD and AWS Nitro, they have some 86%, and Intel SGX have some 88%. So what happens in with this memory intensive workloads is, this is where there will be some real difference. Okay, so TDX stays strong at 78%, but when it comes to Intel SGX, it drops dramatically to 27% when it comes to performance. That means like 74% loss in downside. Like why? Because these workloads which keep hitting this cache limit, it will try to constant swapping in and out. So from this the performance will get down. So for when it comes to AI inference specifically, which we really care about, is that virtual based T shows some 14% up, which is the gray bar in the middle. So this is actually quite impressive, right? Like it means your interface might take some 100 to 112 to 115 milliseconds instead of some 100 milliseconds. That means most of the projects or most of the applications can tolerate that. So the main thing here was that 10 to 25% range for VM based Ts, which is acceptable only for some AI workloads. Like you are not too much sacrificing for the performance or for the security, but for the benefits that you are gaining, right? So now here's another thing gets interesting, that how do we coordinate all of this in a decentralized network? That's where blockchain comes in, right? So when we look at this gas cost optimization, which is the main part, even if you do full chain verification like ECDSA signatures and validating some certificate chains or verifying PCR values on the blockchains, like it's how much, 96,000 gas limits. So typical Ethereum prices, that's almost like an $14 per attestation, right? So what happens when we optimize like hybrid off-chain verifications, which drops it to 46,000 gas, that's almost like $6.90. Still expensive for like even if we have thousands of nodes. But when we look at the Merkle tree batching, if you have some 100 attestation together, the per attestation cost drops almost to 1600 gas, which is like 0.23 cents. That's a 99% reduction in cost. So and those layer 2 solutions are like Arbitrum or even Optimism, which are the L2 chains of Ethereum. So you're looking at just like 0.08 to $0.14 per attestations. So that's how you make this economically viable at scale. I also explained a detail when it comes to gas cost of comparison in the previous videos also. I have linked below in the description. You can check those out too. So in here, let me try to break it down. When it comes to like full chain, it costs like $27,000 per day. Hybrid $6,900 per day. Merkle $233 per day. Layer 2 solutions $120 per day. There's an like difference between this impossible and the actual deployable. So the optimized approaches give you like 99% cost savings while maintaining security through proofs and fraud detections. Even we don't know that Sentient going to use how. Even Sandeep Nainwal, who is a co-founder of Polygon, he is the one who founded Polygon also, which has some great gas cost optimization. That is the first ever project in the entire Ethereum network who made the gas cost optimization very low. So all these Arbitrum optimism took inspire from them, and they made some changes and they built. Okay, so the first project that came was Polygon. So the hybrid TMCP architecture, let me explain this. So this is something like advanced. Even I took some time to understand this. So this diagram shows a hybrid TMCP architecture. Okay, that means instead of trusting one enclave with some complete model, it tries to split 3 different enclaves using a technique called Shamir secret sharing. Okay, so like how we have T node 1 running on AWS Nitro or Intel TDX, and node 3 like AMD. Each one holds some secret share of the model. Okay, not a single node can reconstruct or the complete model on its own. They will be sharing into some three different this one running these nodes. Like when a client sends in suppose an encrypted query, all 3 nodes perform some partial computations on their shares. So then through a secret multi-party computation protocol, they combine results using some reconstruction. Like you need only 2 out of 3 nodes to participate in that. But one of the good part is that even if an attacker compromises one node completely, they can't steal your model, because they need to compromise another two models out of 3 models, 3 nodes across different vendors, right? So that's way harder than attacking a single platform. But when it comes to the trade-off performance, the hybrid approach is like 5 to 10 times slower than using a single T. But that's still like 10 to 100 times faster than the pure MPC without any some say hardware security also. So even when we look at the high value models where security is paramount, it is worth it. So the main takeaway, like let me give some summarizes that VM virtual based TEs like AWS Nitro, AMD, Intel, they are all practical for deploying AI models like 7 to 13 billion parameter range. Okay, but when it goes to high, it takes some challenging part. So process based TEs like Intel simply don't have enough memory for some this modern language models. Okay, so the performance overhead, which is like 10% to 25% for AI inference and TEs, which is acceptable. Okay, for most of the use cases, which is getting like we are getting some security guarantees for some performance cost. So another thing is like the quantization from FP16 to INT8, it was good. Like it cuts your memory requirements in half while maintaining good accuracy. What makes it difference is that impossible to deploy, and it also works great. So this blockchain integration is also expensive when it comes to starting things, but optimized approaches like Merkle trees or batching or even layer 2 solutions with Polygon and all, they can reduce up to 99%. This makes huge scale decentralized AI networks even usable. So when it comes to deployments across multiple TE platforms, as the TE architecture explains, by having 3 different structures, nodes and all, so which eliminates single points of trust. That means this TE MCP approaches some strong security. They have some 50 to 50x performance cost. There are still centralized trust defenders, particularly like AWS or AWS controls. When it comes to attestation keys, this is fine. Okay, like for many use cases, but it's something aware that we need to be maximum decentralization. But right now it's not 100% decentralization. We can't say that, because here they are depending on some other nodes, like some other cloud providers like AWS. Okay, but when it comes to decentralized project, then more example, if you took at like Bitcoin, which is an mining thing. Okay, so anyone can mine, and anyone can provide this mine Bitcoin, right? Which is an entire decentralization concept. But here it's like an almost decentralization, but not entire decentralization, because it is depending on their AWS. For practitioners, like when we build these systems, like we can try to build with some single T platforms for simplicity, and we can also optimize these models also, and we can also implement some attestations off-chain via off-chain as well. So this TEE, that means trusted execution environments, they provide some practical foundation for some decentralized AI. Like they are not perfect, but they are side channel vulnerabilities, centralized trust funds, and they have some even ongoing research challenges also. Don't know what they are going to do in the future as well, but they enable something that wasn't possible before. That means trustless AI inference in decent networks, which is a good work. So the Sentient Enclaves framework, which I analyzed and represents some concrete implementations of these principles. Okay, so if it's truly fully open source, built on AWS Nitro, and shows that this technology is ready for some production, like many can use, not for some distant future. So what I say is that decentralized AI networks where anyone can contribute to compute resources, where model providers can monetize their work safely, or where users' privacy is protected by hardware rather than just promises. That means we are depending on some big tech companies for AI infrastructure. I think we are still earning, but the foundations are solid. Okay. If you are working in this space or just curious or intersections about like AI, blockchain, and security, I hope this deep dive about TEE was helpful. So all the technical details, benchmarks or analysis are in my full paper. Okay, you can check the description. I published it on Zenodo as well. Thanks for watching. This was just a small contribution to the Sentient team by explaining the technical things. Okay, most of the time what I saw is like having some tweets where we can't explain this entire architecture and all. So I try to explain by making in video. I hope you guys understand what I'm trying to say. Let's go with the next video.